Good morning. In the next three lectures, we are going to revise Unit 3, which is electrical installation. In the first video, we are going to discuss about a transformer. In the next video, we are going to discuss about a DC machines. And in the final one, we are going to discuss about the AC machines, which are induction motor and synchronous generator. The first machine, transformer. First, we discussed about the construction and working principle of a single phase transformer. Next, we discussed the types of transformer and we classified transformers based on the operating voltage and based on the construction. Based on operating voltage, there is a step up and step down transformer, and based on the construction, core type and shell type. And next, we derived an expression for EMF induced in the primary winding as well as in the secondary winding. And next, we discussed about the losses in a transformer. As transformer is static device, there are no rotating parts in a transformer. There are no mechanical losses in a transformer. Only electrical losses are present. Electrical losses are classified into two types: iron losses, copper losses. Iron losses are again classified into hysteresis losses, eddy current losses. And next thing we discussed is the equivalent circuit diagram of a ideal transformer under load and no load condition. Similarly, equivalent circuit diagram of a practical transformer under load and no load condition. Finally, we compared the ideal and practical transformer. And in the next half of a transformer, we discussed about a three-phase transformer. The entire this section is about a single phase transformer, and this section single phase transformer. In a three phase transformer, we have only two concepts according to the syllabus, which is a three phase transformer construction and three phase transformer connection. And finally, advantages of a three phase transformer over a single phase transformer. These are the contents. Transformer. Definition of a transformer is: a transformer is a static device which transfers power from one circuit to the other circuit. As transformer does not have any rotating part, the transformer is called as a static device, and it is also called as a constant frequency device, constant flux device, because the frequency of input side is equal to the frequency of an output side. As frequency is maintained constant throughout the process, so it is called as a constant frequency device, and it is also called as a constant flux device. Moving on to the construction of a single phase transformer. There are three major parts in a transformer. The first one is a primary winding, second one is a core which is made up of a steel, and the third one is a secondary winding. Both primary winding and secondary winding are made up of a conducting material as it carries a current, so they are generally made up of a copper. Whereas a core is not intended to conduct electricity, it is intended to conduct flux, so it is made up of a steel. and N1 represents the number of turns in the primary winding and N2 represents number of turns in the secondary winding. Moving on to the working principle of a transformer. Transformer works on the principle of mutual induction. Mutual induction. Suppose assume there are two coils one over the other. Let's suppose you applied a AC supply across one of the coil. A flux is induced by the coil 1. This flux links coil 2. As coil 1 and coil 2 are near to each other, this induced flux links the secondary coil and in turn generates EMF in the secondary coil. So this process is called as mutual induction. One of the applications for a mutual induction in our day-to-day life is wireless mobile charging. If you observe, an electricity is provided to the wireless charging pad, induce a magnetic flux, and if you put your mobile on that induction pad, charging pad, and the coil inside your mobile, which is a secondary coil, interacts with the flux and produces EMF or current inside your mobile and utilizes to charge the battery. This is mutual induction. Similarly, we have two coils, coil 1, coil 2. The coil 1 is excited with the AC supply. If it is excited with the AC supply, a flux will be generated. This generated flux links the secondary coil, which in turn generates EMF in the secondary winding, and this EMF can be used to supply the load. Next concept is types of transformer. There are two types of classification. The first one is classification based on operating voltage. Based on operating voltage, transformer is classified into step up and step down transformer. In a step up transformer, voltage is stepped up. The input voltage will be lesser value and the output voltage will be higher value. If you observe, this is a transformer. Here, let's suppose V1 is the applied voltage and V2 is the output voltage. If you compare both V1 and V2 in a step up transformer, you can observe that V2 is greater than V1. V2 is greater than V1 and N2 is greater than N1. Similarly, for a step down transformer, the voltage is stepped down from primary to secondary, which means the primary winding will have a higher voltage and the secondary winding will have a lower voltage. So V2 is less than V1 and N2 is less than N1. And the next we classified transformer based on the construction, which is a core type and shell type, and I gave you the diagram for a core type transformer and a shell type transformer. Next concept is EMF equation of a transformer. Now let us consider a transformer where N1 is the number of windings in the primary, N2 be the number of windings in the secondary, and V1 is the primary voltage and V2 is the secondary voltage, and phi be the flux in the core. And according to the Faraday's laws of electromagnetic induction, which you learned in the first unit, induced EMF in the winding E equal to minus N into d phi by dt. As we already know the expression of a flux phi equal to phi m sin omega t, if you substitute phi equal to phi m sin omega t in the above expression, you will get the final expression E equal to n1 phi m omega t sin omega t. But if you observe, this is a time domain expression. This expression is with respect to time. As E1 is an alternating voltage, we are going to represent the alternating voltages with a RMS value. We are going to represent the DC voltages with the average value, but as this expression is an RMS value, we are going to represent the induced EMF in an RMS value. So to calculate RMS value, first we need to find the maximum value. The maximum value occurs at omega t equal to pi. We substituted omega t equal to pi and we got a maximum value for a induced EMF in the winding 1, which is equal to n1 phi m omega t. If you substitute omega 2 pi f, the final expression you will get E max equal to 6.285 m Fn, and we know the relation between RMS value and a maximum value, which is ERMS equal to Emax by root 2. So and finally we got induced EMF in the winding 1 in terms of RMS, which is equal to 4.44 phi m Fn1. Similarly, for the induced EMF in the secondary winding, RMS value equal to 4.44 phi m Fn2. So we can generalize the expression as E equal to 4.44 phi Fn, where phi is the magnetic flux, F is the frequency, where N is a number of turns. And moving on to the next concept, losses in a transformer. As transformer is a non-rotating machine, there are no mechanical losses in a transformer. There are only electrical losses, which are iron losses and copper losses. As we discussed, iron losses are classified into two types: hysteresis and eddy current losses. Hysteresis losses are due to hysteresis loop. We need to maintain coercivity and retentivity of a material. We have to choose a material such that coercivity and retentivity of a particular material is very less. So in order to reduce coercivity and retentivity, we added a silicon. We added 3 to 4% of silicon to the steel and used as a core. And the expression for hysteresis loss is equal to zeta B max power x F into V. Moving on to the eddy current losses. Eddy currents are unwanted currents which occur in the core due to the flux linkage. To reduce these eddy current losses, we are going to laminate the core. Generally, the laminations are in millimeters. And the expression for eddy current losses is equal to KB max square F square V square T square. Finally, the copper losses. Copper losses are due to the resistance of a winding. So the expression for a copper losses is W equal to I square R. And we also saw the expression for the efficiency and voltage regulation in a transformer. And the next concept is equivalent circuit diagram of a transformer. First, we drew equivalent circuit diagram of ideal transformer. For an ideal transformer, there are no losses, there are no hysteresis losses, no eddy current losses. So simply we are going to draw a supply and draw primary winding, and secondary winding is connected to the load. Whereas coming to the practical transformer, under no load condition, where a load is not connected at the secondary winding, under no load condition, the current in the winding is almost zero. So as current is zero, copper losses are not present, so copper losses is equal to zero. No need to represent the copper losses in the circuit diagram. But whereas coming to the iron losses are proportional to the voltage, as there is a voltage connected in the primary winding. So core losses are present. These core losses are represented with this resistor and inductor in parallel. Coming to the equivalent circuit diagram of a practical transformer under loaded condition, as a load is connected, a reasonable or considerable amount of current flows in the winding 1 and winding 2. As current flows in the winding 1 and winding 2, there are copper losses present in the primary winding and secondary winding. So under loaded condition, there are both copper losses in the primary winding and secondary winding and iron loss. Moving on to the next half of unit, which is a three-phase transformer. The first concept in a three-phase transformer is construction of a three-phase transformer. We can construct a three-phase transformer in two ways. The first one is using three single-phase transformer. In the first half, we discussed a single phase transformer. Just take three of those single phase transformers and connect it to R phase, Y phase, B phase. Simply we can make a three phase transformer. But problem with that type of a construction is, for that type of a construction there are more amount of losses present, both hysteresis losses and eddy current losses as well as copper losses. So in order to eliminate those losses, we are going to choose a different type of constructional approach where we are going to embed three windings R phase, Y phase, B phase onto a single bank in a single construction such that the losses are reduced. This is a simple circuit diagram for a three-phase core type transformer, and this is for a three-phase shell type transformer. Moving on to the wiring connection. The winding connections are of four types: star star, delta star, star delta, and delta star. The first one, a star star. Primary side is connected in a star format, and the secondary side is also connected in star format. Whereas coming to the star delta, the primary side is connected in star and the secondary side is connected in delta configuration, and so on. So in class I explained how to make connections, how to connect three single phase transformers in star connection and in delta connection in class. Just follow the notes. And finally we discuss the advantages of a three phase transformer over a single phase transformer. These are the advantages and disadvantages of a single phase transformer, three phase transformer over a single phase transformer. So in conclusion, first read the construction and working of a single phase transformer, then move on to the losses of a single phase transformer, and next study practical transformer under loaded condition, and finally a three phase transformer construction and connection. As we have only two concepts in a three phase, this section is most important. And a definition of efficiency, voltage regulation, turns ratio, transformer ratio. From this section there is a possibility for a 2 marks question. And next study classification of transformer based on the operation and construction, EMF equation, and finally the comparison of ideal and practical transformer.